This documentary is for educational and historical purposes only. All information is based on publicly available data, open source reports, and widely accepted aviation analyses. No new evidence is introduced. Our deepest condolences remain with the families of MH370. Malaysia Airlines Flight MH370 was operated using a Boeing 777-200ER, one of the safest twin-engine aircraft ever built. Its serial identity was precise. Manufacturer serial number 28420, line number 404, registration 9MMRO, ICAO hex code 75009F. Powered by two Rolls-Royce Trent engines, the airframe held an excellent operational record. At 12:42 a.m., MH370 lifted off from runway 32R on a pre-planned route toward Beijing. Weather was stable, winds were calm, and all technical systems were functioning normally. At 1:19 a.m., moments after entering Vietnamese airspace, the cockpit transmitted the final known words, "Good night, Malaysian 370. Technically, this message aligned with the normal handover protocol from Kuala Lumpur Control ATC to Ho Chi Minh Control ATC. There was no sign of stress, system fault, or crew confusion. It was a calm, professional transmission, the last confirmed human communication from the aircraft. This video delves into the critical technical details surrounding its vanishing, focusing on the shutdown of its communication systems. We will examine the sequence of events involving the Aircraft Communications Addressing and Reporting System, or ACARS, and the aircraft's transponder, known as Automatic Dependent Surveillance Broadcast, or ADSB. At 1:07 a.m., MH370 transmitted what would be its final routine ACARS message, a standard engine health report sent through the Rolls-Royce monitoring system. After this transmission, something changed. The aircraft's data link fell silent. To understand the significance of this silence, we must understand how ACARS works on a Boeing 777-200ER. ACARS is responsible for delivering performance metrics, position updates, and system health reports using multiple communication pathways, VHF, HF, or SATCOM. On Malaysia Airlines MH370, SATCOM through the Inmarsat-3 Indian Ocean Region satellite was the primary channel. This means ACARS cannot simply be turned off with a single switch. But investigators found that while ACARS message traffic ceased after 1:07 a.m., the SATCOM terminal remained active, continuing to send automated hourly handshakes. These digital pings are not intentional messages. They are background system checks that reveal something crucial. The satellite terminal was still powered, still functioning, and MH370 was still airborne. The selective loss of ACARS transmissions is therefore significant. It indicates the suppression of data messages, not a catastrophic system failure. On the Boeing 777, this selective disabling can be done in two ways from the cockpit. Option 1. using the CDU FNC COM menu to deselect ACARS uplink or downlink functions, essentially silencing its data channel. Option 2. Pulling specific circuit breakers on the P6 and P18 overhead panels. While not commonly accessed during normal flight, they remain reachable from the flight deck. Importantly, neither method requires entering the avionics bay beneath the cockpit, a misconception often repeated in online speculation. MH370 did not lose all communication capability. Instead, it stopped sending the type of data that reveals location and system health. It went dark by choice, not by accident. And that choice changed the investigation forever. Minutes after ACARS fell silent, another crucial system disappeared. MH370's transponder. This device is not just a transmitter, it is the aircraft's digital identity. Through Mode S extended squitter, it sends altitude, identity, and velocity data to civilian secondary surveillance radar systems. At 1:21 a.m., this transponder stopped broadcasting. It did not degrade. It did not fail. It was manually switched off. On a Boeing 777, the transponder is controlled by a simple rotary knob on the center pedestal, allowing it to be set to on, alt, standby, or off. Moving it to standby or off removes the aircraft instantly from civilian radar screens. But MH370 did not disappear entirely. Military primary radar, which detects raw reflections rather than identity codes, still tracked a target. This unidentified echo revealed something remarkable. MH370 turned back. It made a wide, controlled left-hand turn across the South China Sea, then crossed the Malay Peninsula. The turn was smooth, showing stable bank angle and controlled airspeed. Radar reconstruction suggests that the aircraft followed a navigationally precise path, behavior inconsistent with catastrophic failure or pilot incapacitation. The aircraft flew past Penang, then continued northwest into the Strait of Malacca. Its path aligned with known airways, possibly indicating an intentional effort to remain within predictable corridors of traffic. This sequence of events is critical. For an aircraft to disable ACARS selectively, switch off the transponder manually, execute a deliberate turnback, and fly accurately along airways, all without a single distress call, suggests a controlled and purposeful sequence of actions. The mystery deepens here, because MH370 did not simply vanish, it navigated. The technical details surrounding MH370's disappearance paint a picture of intentionality, leaving us to ponder the unanswered questions that continue to haunt the aviation world. Flight MH370 followed its planned route until reaching Igari Waypoint, approximately 01:21 Malaysia time. Around this time, the aircraft's ACARS system ceased transmitting automated messages. ACARS, or Aircraft Communications Addressing and Reporting System, normally relays engine parameters, fuel levels, and navigation status to ground stations. On the Boeing 777-200ER, this system can be disabled via cockpit controls or power circuit breakers, stopping all automated transmissions without physically entering the avionics compartment. This action effectively prevents routine monitoring while leaving the aircraft otherwise flyable, a rare but feasible technical scenario. After ACARS transmission stopped, primary radar detected a turn back towards the northwest at approximately 0121 Malaysia time. The aircraft deviated from its filed flight plan, suggesting manual inputs or autopilot reprogramming. The transponder remained active for a brief period, providing intermittent secondary radar signals before complete radar disappearance. Analysis of this segment indicates controlled maneuvers consistent with a competent operator using onboard navigation systems while communications remained offline. After executing its unexpected turnback, the aircraft crossed the Malaysian peninsula on a westbound track. Primary military radar recorded several heading adjustments, suggesting the flight was under controlled navigation rather than drifting. The Boeing 777's flight management computer allows rapid route modifications using waypoint insertion or direct-to headings, all achievable within seconds by an experienced operator. During this phase, radar returns indicated changes in altitude between 29,000 and 35,000 feet, though the precision of primary radar is inherently limited. The varying altitude readings, combined with the stable lateral navigation, imply deliberate flight inputs rather than uncontrolled flight dynamics. Its westbound transit across Malaysia required the aircraft to pass near busy airspace corridors. Yet, with the transponder inactive, the aircraft remained invisible to civilian ATC systems, relying solely on military primary radar reflections for detection. Upon reaching the vicinity of waypoint Mekar, the aircraft continued northwest into the Andaman Sea, entering one of the least monitored airspace regions in Southeast Asia. At this stage, the flight was no longer tracked by Malaysian primary radar, and no Thai radar returns were formally recorded, suggesting the aircraft moved through an air defense gap that requires manual radar activation to detect low-priority tracks. The Boeing 777, cruising at roughly 480 to 510 knots, would have covered this segment quickly. With the transponder off and ACARS inactive, the only potential source of data would have been satellite systems. This is the point where analysts later correlate the aircraft's path with early Inmarsat handshake signals, indicating the aircraft was intact, powered, and continuing flight over the remote waters of the Andaman Sea. This entry into the Andaman marks the transition from radar-supported tracking to reliance entirely on satellite-based communication timestamps, fundamentally reshaping the investigation that followed. With radar coverage lost as the aircraft moved northwest, the investigation pivoted to a far more unconventional data source, the Inmarsat satellite network. Normally, the system handles routine ACARS transmissions, but even with ACARS disabled, the aircraft's satellite terminal remained capable of performing automated log-on handshakes. These periodic exchanges, called pings, established nothing more than that the aircraft was powered and its satellite terminal was functioning. However, engineers discovered that each handshake contained two measurable properties, or the burst timing offset, or BTO, indicating the approximate distance between the aircraft and the satellite, and the burst frequency offset, or BFO, which provided clues about the aircraft's motion relative to the satellite's position in geostationary orbit. By plotting these BTO arcs and analyzing the Doppler-shifted BFO data, investigators determined that the aircraft followed one of two possible corridors, one northbound towards Central Asia and one southbound into the remote Indian Ocean. The frequency drift analysis later eliminated the northern route, pointing conclusively toward a long, uninterrupted southern trajectory. This technical breakthrough transformed a mysterious disappearance into a mathematically constrained search corridor, extending thousands of kilometers into open ocean. After the final radar point near the Andaman Sea, the aircraft is believed to have initiated a long, continuous turn toward the southern Indian Ocean. This maneuver, inferred from the first post-radar Inmarsat handshake, suggests deliberate route selection rather than drifting flight. A Boeing 777's autopilot offers multiple navigation modes capable of maintaining track, altitude, and throttle parameters for many hours, even after the loss of crew input. The southern path is consistent with the Doppler analysis of the burst frequency offsets, which revealed a downward trend characteristic of an aircraft moving steadily southward, away from the satellite's equatorial position. Calculations involving geodesic curvature, Earth rotation, and satellite geometry were used to derive the most likely track, narrowing the corridor to a band extending deep into the Indian Ocean. This part of the world is among the most remote on Earth, with sparse radar coverage, limited maritime presence, and vast stretches of unmonitored sea. The aircraft could continue in stable cruise for 6 or more hours until fuel exhaustion. The final satellite handshake, occurring near 19 UTC, marked the end of available data, corresponding to a drastic drop in engine power during fuel depletion. At this stage, only complex ocean drift modeling and seabed mapping could approximate the aircraft's final descent. The final Inmarsat handshake, occurring at 00:19 UTC, offers the most crucial technical clue about the aircraft's last seconds of flight. Unlike earlier pings, the burst frequency offset of this final signal exhibited an abrupt shift characteristic of an engine flame-out scenario. When fuel exhaustion occurs, the Rolls-Royce Trent 800 engines spool down asymmetrically, causing changes in electrical load, vibration patterns, and power delivery to the satellite terminal. As the aircraft lost thrust, it likely transitioned from stable cruise into a descent driven initially by aerodynamic glide and eventually by uncontrolled aerodynamic instability. Engineers observed that the BFO anomalies match simulations of a 777 descending without active autopilot inputs after fuel depletion. This implies that at least at the very end, the aircraft may not have been under human control. The seventh arc, derived from this final handshake, forms a curved line thousands of kilometers long, along which lies the estimated position where the aircraft intersected with Earth's surface. Because fuel depletion reduces engine-driven generator output, the aircraft's SATCOM rebooted briefly before final power loss, explaining the short, final log-on attempt captured by Inmarsat. These last digital traces mark the end of MH370's airborne life. Beyond this point, only oceanographic drift models and deep-sea search technology could attempt to locate the aircraft's final resting place. The disappearance of MH370 triggered one of the most extensive and technologically challenging search missions in aviation history. Using autonomous underwater vehicles, synthetic aperture sonar, and high-resolution bathymetric mapping, search teams surveyed more than 120,000 square kilometers of some of the world's most hostile ocean floor. The southern Indian Ocean features deep trenches, abrupt underwater escarpments, and shifting seabed sediment, conditions that severely complicate sonar interpretation. Yet the search produced valuable data. Several pieces of confirmed MH370 debris, including a flaperon discovered on Reunion Island. These pieces were later matched with serial number analyses, material forensics, and paint layer signatures consistent with Boeing specifications. Oceanographers used complex drift modeling based on the Leeway model and satellite-tracked buoys to analyze how floating debris traveled from the seventh arc to coastlines in Madagascar, Mozambique, and Tanzania. These models reinforced the southern route conclusion and narrowed the likely impact region. Despite multinational cooperation and advanced robotics, the main fuselage and flight recorders remain undiscovered. The absence of conclusive physical evidence leaves room for multiple theories, but only those supported by measurable data remain credible. MH370 stands today as both a technical puzzle and human tragedy, reminding us of the vastness of our planet and the limits of modern tracking systems, and also as human being compared to greatness of God. While the mystery persists, the search efforts represent an unprecedented union of satellite science, oceanography, radar analytics, and global engineering. But ultimately, only God knows what truly happened in those final moments. The story of MH370 is far from forgotten, and the quest for answers continues. Our prayers remain with them forever.